No, I think we stopped at I know I don't fully follow the what Jackson did, 11.4, but we finally wrote down the what we call the fall velocity, right? And you remember that this is for a single particle. So the fall velocity is instead of the just the usual velocity, you get the gamma, and then this is a four vector. So you have the spatial part, spatial part basically C. This gamma is the particle's gamma, so it's gamma sub u, and then the velocity. Right, we got what we call the four velocity. Okay, and so this is a four vector, so you know how to transform it, and based on that, you can work out the transformation of u. And then also obviously gamma u also, and that's consistent with the other method to divide that. So we are slowly building up our collection of four vectors, and now we get to this four velocity. Now we do the next thing is energy and momentum of particle, and just again using a more complicated or maybe more rigorous way to divide that. But we don't have time for all these. We do it in a simplified way. We just by looking at suggestion. So basically, now to get the momentum, we notice that there's a velocity, although there's a gamma, but we multiply by the mass of the particle anyway. And obviously, in the limit of a small velocity, basically u is much smaller than c, then that gamma becomes 1. That becomes m times c and m times u. The n times u is obviously, remember this is the momentum, mc, and momentum of the particle. Okay, so that's at least there's a suggestion that this actually should be this m times gamma times u is the relativistic part of the momentum, at least because it's in non-relativistic limit. Get back to the ordinary momentum. So that's a suggestion, and to make it slightly more rigorous, and because this is four vectors, and you need to figure out what this in this limit in the non-relativistic limit is the first component, the so-called time component. Go to m times c, both are constant, so that at first you don't recognize what that is. The reason is that we are missing something when we take the non-relativistic limit. We probably need to do this limit in one more order. Instead of just all the way setting gamma to 1, we want to keep one more order in this small parameter in the u expansion. So let's do it and see if we can see the suggestion what that should be. So instead MC, there's something else. So let's see, gamma u, just write it down. 1 minus u squared over c squared, right? Now instead of just setting it to 0, we're using the binomial expansion. That is approximately 1. This is a minus 1/2 factor, so you minus 1/2 and multiplied by this small parameter, which is minus u squared over c squared, which is 1 plus u squared over 2c squared. Okay, now we multiply by m. Multiply by m first, m gamma u. Okay, so just the first is just m. Right? I actually there's a c, m gamma u c, mc, and then plus m 1/2 m over u m over 2 u squared over c. Right. Now we take the c common denominator, c out over c, that becomes m c squared plus over 2 u squared. Okay, then now you can recognize this part. This part is just this part is just the kinetic energy, right? And so this component has two parts other than this MC. You actually MC the first part MC, but then you plus the kinetic energy divided by C. Okay, then that's and this is just a constant. Basically, you have kinetic energy plus a plus just what we call this just a constant. So whatever that is, it does, because usually when we talk about energy, just most the concerning is the difference between energy. So adding a constant doesn't change the difference. So so you can still say this, the total thing is energy. So we can say this is energy divided by C. Okay, so that is a suggestion, but then it turns out to be correct. So energy and momentum form of forward energy divided by C. And to make it dimensionally correct, I mean, sometimes people work in relativity usually just says C equals to 1. So that makes all the writing easier. But anyway, this energy and momentum together form a four vector. Okay, so that is and the energy now write like that energy is there are two parts. That is mc squared plus m, but the usual kinetic energy in the non-relativistic limit. Actually like E is down the mc squared. Approximately this in the non-relativistic limit. Okay. So there's a kinetic energy plus some kind of a constant. And so that is the basis for the, obviously, for the famous formulas. E is mc squared. Right? That is how you get from it. At least I suggest, I mean, Jackson used a more complicated way to divide that. But anyway, that is at least how we suggest that energy and momentum form a four vector. And one more thing is that this m in all these in the derivation, I treat it like a constant. So that is what we call a scalar that is independent of inertial frame. We treat m as a constant. And the old language, or I mean the old convention would say that the mass actually changes with frame, and then when it's moving, it has the mass is gamma times m. Okay, it's increasing. If you are moving, a particle that is moving has a largest mass, but mass increased by a factor of gamma. So that is, I mean, that is another way to look at it, but it's kind of like old convention. Most people now treat the mass, the intrinsic mass of a particle, as a scalar, which is independent of frame. It's just the energy change with according to this gamma times mc squared. So that is what changes, the energy that is changed. Obviously, but there are other situations that you can say that the mass actually is changing, like what we call the binding energy. The usual binding energy in a chemical reaction is very small, but in nuclear interaction or nuclear reaction, the binding energy can be in the order MeV, which is significant. It's not large fraction, but then if you consider like if you have a neutron, and then separate into two parts. That's like the usual fission reaction to some larger nuclei. They can separate into two or more, and so if you combine the mass of these all these products, you see that this actually is less than the mass of this nucleus. So the difference in mass would be the energy released by this particle. So this particle will move out with certain energy, and that energy is the mass difference and times the c square, and so that is what we call the binding energy. Okay, so in this sense, you can say that mass mass is equivalent to energy, and also that what we call the mass of intrinsic particle actually can actually be kinetic energy or interaction energy, or the combination of both. Like even what we consider like a elementary particle like a proton or a neutron, they actually have something inside. Like a proton, you usually have using the quartz theory, you have two up chord and one down, and then they interact crazy. Yeah, they are glued together, what we call by the gluon, and they are. And the calculation for the partition of all these different components is difficult to do. This is using the what we call QCD to do that. But most of the energy actually turns out to be the gluon energy. So the energy actually becomes the mass of the particle, because this is all within the particle. So, but after you calculate everything, you just say the proton has a certain mass, but the mass actually is due to the energy within the proton, the components of the particle. Okay, so there are many strategies of this what we consider mass, but in the context of a part, just what a particle, we usually like to consider is as a scalar independent frame, because we want to actually write equation of law or physical law in terms of quantity that is independent of frame. We want to classify things like that. So mass as a scalar becomes a more acceptable concept. Only that the energy and momentum form a four vector, which is also an invariant way to write law of physics. Okay, so that is that energy and momentum for vector. And there's another connection. Last time we already derived that frequency of a wave and the wave vector of a wave also form a four vector. You remember that. This is due to the fact that we derive that by the fact that the phase of the wave is invariant, and the phase is omega times t plus k dot x. So, and then by the fact that the space-time four vector, the space-time combined to four vectors, so the frequency and wave number also combined to four vectors. Okay, and you can also connect this to the energy momentum four vector, because in quantum physics you consider particle as both a particle and wave. There's a wave property, so you multiply by h bar for the wave of the particle, and that becomes like h bar times omega is that energy, h bar times k is the momentum of the particle. So in that sense, you just multiply by another difference, convert this four vector to the other four. Okay, so there's the other the other relation that you can get to this energy momentum forward. Okay, so let's see here. Once you have this energy momentum forward, of course, you know how to do the transformation. They just use the Lorentz transformation, and also with this forward, you can define the norm. And the norm actually is sometimes useful because the norm base is a scalar and independent of frame, so that is sometimes very convenient in doing calculation. So the norm for a particle, we are using that. So m the energy momentum forward is the norm becomes m everything squared times gamma c squared, and then the minus m. This is actually, as you say, this is m gamma squared. Actually, code everything squared. That is a constant. Okay. So, and you can further simplify that because you have gamma u here. Get the gamma u out. Actually, m also m squared, gamma u squared. And the rest is, you can take the c squared out. 1 minus u squared over c squared. And you recognize this is just one of the gamma squared. So this is just m squared c squared. And that convinces yourself that this norm of this forward is indeed a scalar because both mass is considered that as a scalar. The speed of light is just a constant. Okay, so that is independent of frame.